Hello everyone, welcome to my channel. Let's learn computer science. Hey everyone, welcome back to my channel. In our previous lesson, we learned about machine code and assembly code. But a very important question still remains. How does an assembly language program actually get converted into machine code that the CPU can understand? Well, that's exactly where today's session is all about. Assembler stages. Two-pass assembler basically. In today's video, you'll understand what an assembler is, why assemblers are needed, single pass and two-pass assemblers, forward references, symbol tables and opcode tables, and finally how a two-pass assembler converts assembly language into machine code step by step. Alright, so let's begin. First of all, let's understand what is an assembler. An assembler is a system software program that translates an assembly language program into machine code. Remember, the CPU cannot directly execute instructions like LDD 100, add 200, or JMP, something something. The processor only understands binary instructions made up of zeros and ones. So, assembler acts as a translator between the programmer and the processor. But an assembler does much more than simply translating. It also checks the syntax of assembly language program, ensures only valid opcodes from the instructions set are used, detects errors before execution, produces machine code instructions for the processor. So you can think of an assembler as both a translator as well as an error checker, right? So there are mainly two types of assemblers, single pass assembler and two pass assembler. Let's understand each one. As the name suggests, a single pass assembler reads the source code only once. As it reads each instruction, it immediately converts it into machine code. The generated code is usually placed directly into memory so that it can be executed immediately. This approach is very fast because the source program is scanned only once. However, there is a limitation. Single pass assemblers cannot easily deal with something called forward references. And this is the main reason why two pass assemblers are widely used. What is a forward reference? In assembly language, a label may be used before its address is known. For example, here in this example of assembly language, there is a label not found here. There is a label found here. Okay, so just consider this instruction JPN found. At the moment when assembler reaches here, it has not yet read the line found out where the actual label is mentioned. So the assembler does not yet know the memory address associated with the label found. This is called forward reference. When you are referring to the label, but actually you have not reached there yet. Assembler has not reached there yet. So this is called forward reference. A two-pass assembler solves this problem by finding all labels and their addresses in pass 1 and replacing these labels with actual addresses in pass 2. So, a two-pass assembler basically reads the source code twice, creates an object program that can be stored and executed later, uses a loader to load the object code into memory before execution, and can handle forward references using a symbol table. Before the actual assembly process begins, some preparatory work may take place by the assembler, like removing comments. Suppose we have LDD 100 and there is a comment called load value. So everything after semicolon is a comment in assembly language, okay? So comments are meant for humans, the programmers, for documentation purposes, and not for the processor. Therefore, the assembler ignores them, right? And also may expand macros. Sometimes programmers define a macro. A macro is simply a shortcut representing multiple instructions. So the assembler replaces the macro name with the complete sequence of instructions. Assembler also processes directives, and directives are special instructions that guide the assembler rather than the CPU. For example, directives may specify where the program should begin in memory. Okay. Now let's see what actually happens during pass 1. The assembler during the pass 1 reads the program line by line. During this stage, it performs several tasks. It reads each line of the source code. It ignores comments and unnecessary information, allocates memory addresses to instructions, checks that each opcode exists in the instruction set, identify tables, create and update the symbol table, store the address of each labeled instruction. Notice something important. No machine code is generated yet. The main purpose of pass 1 is to simply collect the information. Okay. So main output of pass 1 is a symbol table containing labels and their addresses. Now what is a symbol table? A symbol table basically stores labels along with their corresponding memory addresses. For example, label not found, it is saved at memory address 100, found is saved at memory address 104. Later, whenever the assembler encounters the label found, it can simply look up at address 104 in this table. Very convenient, right? After completing the pass 1, the assembler starts pass 2. This time, it reads each instruction, looks up binary values of opcodes, searches the label address of the symbol table, replaces labels with actual addresses, generates machine code, produces the final object code, and of course save the object program for loading and execution. Now, if you look at what is the main output of pass 2, it is an object program consisting entirely of the machine code. Okay. And a two-pass assembler, it uses few tables, mainly symbol table and opcode lookup table. Now, symbol table, it stores labels with the memory locations, like all the labels on one side and their addresses on other side. And opcode lookup table, it stores machine code equivalent of assembly mnemonics. So this is the opcode and its equivalent binary code. Okay. Whenever the assembler encounters an instruction, it searches the table to obtain the machine code for that particular instruction. Okay. Now, let's have a look at this assembly program. There are few instructions written in, sub, store, LDM. All these instructions are written here. Just have a look. Now, how this program is converted into machine code using a two-pass assembler, let's have a look. So, during pass 1, the assembler counts instruction locations. As it scans the program, it encounters labels like str, TLP, max, total, count. These are stored in the symbol table. Okay, so a symbol table is created. The resulting symbol table is right in front of you. Again, remember, no machine code is generated yet during pass 1. During pass 2, once the pass 1 is over, pass 2 will begin. Now, the assembler will use the opcode lookup table. It will use the symbol table. It will replace labels with their actual addresses. So, suppose the assembler encounters CMP max. First, it look up CMP in the opcode table, and then it finds its equivalent machine code. Then it searches the symbol table for max, and address is located for max. So the final machine instruction will become like this in binary. And this process continues for every instruction in the program. So final output at the end of pass 2, the assembler will produce an object program containing only machine code. So this machine code then can be stored on secondary storage, loaded into memory by a loader, or executed by the CPU. So let's have a look at the summary of two-pass assembly process. So during pass 1, assembler reads the source code, check opcodes, allocate addresses, identify labels, build symbol table. During pass 2, it reads source code again, uses symbol table, use opcode lookup table, replace labels with addresses, generate machine code, and produces an object program. So to summarize, an assembler translates assembly language into machine code. And a two-pass assembler is particularly useful because it can handle forward references by first collecting all labels and then generating machine code. Understanding this process is extremely important for your examination point of view. So that's all for today. If you found this video helpful or useful, do like, share, and subscribe to my YouTube channel. That is Computer Science with SKS. Thank you for watching. I'll see you in the next video. Till then, take care and bye-bye.